Okay, my amazing chemistry students. So last time we talked about the different types of IMFs, and we used that boiling point graph to help us understand those different types. Today we're going to talk about the relationship between the strength of IMF and boiling point, and then we are also going to start in on the review. We will finish the review next time and take the quiz, okay? So I'm on page 15 of our guided note packet, and I want us to do a couple of these like starter activities together. Okay, so the first thing I want us to discuss is we had three main types of IMFs. Dispersion forces, or London dispersion, dipole-dipole, and hydrogen bonding. Okay? And so remember from last class that London dispersion forces occur for all molecules, and they are the only ones for non-polar molecules. Now, dipole-dipole happens for polar molecules. And then we have this really strong hydrogen bond. And in order for a hydrogen bond to occur, the molecule needs to be polar, and there needs to be a hydrogen, and so like as a bond inside the molecule, hydrogen needs to be bonded to fluorine, oxygen, or nitrogen. Okay, so like water has hydrogen bonding. Not all the domains are the same, so it's asymmetrical, so it's a polar molecule. And notice how it has a hydrogen and it's bonded to an oxygen, one of these three. So that means it's capable of having hydrogen bonds between another water molecule. So like this attraction between them, the IMF, this could be a hydrogen bond. Okay. The strength of IMF and the boiling point are directly proportional. Okay, so down to the bottom of the page, like boiling point and IMF. So the relationship between boiling point and strength of IMF is proportional, or directly proportional. Okay, directly proportional. So what this means is when the boiling point is high, then the IMF was also high or big or strong. Or if the boiling point is low, that would mean that the IMF was small or weak. Okay? All right, so little reminder here. Okay? We have water, H2O, and these are non-metal atoms. And so the intramolecular, like the bond, if we're looking at this diagram, this is our intra, this is our inter. So the intra is a covalent bond. Okay? So this would be covalent. And if we did that difference in electronegativity, we'd actually see that it's a polar covalent bond. Okay? Now, the entire molecule is polar. And then we have different IMFs that can occur between it. So every single molecule experiences London dispersion. Okay, so London dispersion will always be 1. It's a polar molecule, so we'll also have dipole-dipole. And then it meets the criteria for a hydrogen bond. So we have different IMFs that can occur between these water molecules. Okay. Now, HCl, if I were to draw this Lewis dot structure, this is what you'd see. Okay. So then I'll draw it bigger over here. Hydrogen bonded to chlorine. And there's 3 lone pairs around that chlorine. Okay. So the hydrogen and the chlorine are both nonmetals. And we know that when it's a nonmetal bonded to a nonmetal, that's a covalent bond. And this whole molecule is asymmetry because there's 4 domains. 3 of them are the same, but 1 of them is different. So we got another polar molecule. Okay. So it's a molecule, so it'll experience London dispersion. It's also polar, so it'll have dipole-dipole. But it doesn't meet the criteria for hydrogen bonding. Remember hydrogen bonding? It has to have a hydrogen bonded to a fluorine, an oxygen, or a nitrogen. There is a hydrogen, but it's bonded to chlorine, not one of those items, so it's not going to experience hydrogen bonding. Okay, so looking at these next 2, if I were to draw the Lewis dot structure of NH3, this is what it would look like. And we have another molecule that's asymmetrical. So nitrogen and hydrogen are nonmetals. It's another covalent bond. And this is a polar molecule. Oh, so it's going to be really similar to before, where it's a molecule and all of molecules experience London dispersion, and it's also polar, so it'll have dipole-dipole. Okay. And then our last one here, CH4. So that Lewis dot structure looks like this. Okay. And I see that this is symmetrical because all the domains are the same. So this is a non-polar molecule. So we got nonmetals, so it's covalently bonded, but this is non-polar. So when a molecule is non-polar, the only IMF or intermolecular force is London dispersion. So I don't know what the boiling points are for each of these, but I could make this assumption that since hydrogen bonding is the strongest IMF, and water of this whole list is the only one that has hydrogen bonds, it probably has the highest boiling point of all of these. And since CH4 only has London dispersion, I bet it has the smallest boiling point of all these because it had the weakest IMF. All right. So, turning the page, looking at page 16. We are going to predict, so for each pair of molecules, think about the type of IMF and predict which molecule in each pair would have a higher boiling point. Let's change it. Instead of just like the type of IMF, let's add the strongest. Because it could experience multiple IMFs, but let's just write down the strongest one. Oh, we just did these ones, so this one's easy. We got a water molecule, which is polar, and it meets the criteria of hydrogen bonding, whereas the hydrogen bonded to either a fluorine, an oxygen, or a nitrogen. So its strongest IMF is hydrogen bonds. And then HCl, it's polar as well, but it doesn't have a hydrogen bonded to a fluorine, oxygen, or nitrogen. So its dipole-dipole is the strongest one. So we know hydrogen bonding is a stronger IMF than dipole-dipole. That means the boiling point of water is going to be higher than HCl. So we need to predict which molecule in each pair would have a higher boiling point. Let's circle the ones that we think are going to have the higher boiling point of the pair. So that would have my higher boiling point. Okay, next. We have a polar molecule and a non-polar molecule. So polar molecules experience dipole-dipole. Let's see if it meets the criteria for hydrogen bonding. Reminder, when inside the molecule we have hydrogen bonded to fluorine, oxygen, or nitrogen, then we can experience that stronger hydrogen bonding. So we have, oh, hydrogen bonded to nitrogen. So hydrogen bonding. Okay. Where this is nonpolar, so the only IMF it experiences is London dispersion. Okay, which one is the stronger, the bigger IMF? Hydrogen bonding. So that would lead to a bigger or a higher boiling point. Okay, now we talked about this next one when we went over London dispersion. So both of these are nonpolar. So that means London dispersion is the strongest for both of them. But we can still determine which one's going to have a higher boiling point. So it turns out for London dispersion, and we talked about this in class this time, that the bigger the molecule is, the stronger those London dispersion forces are. So even though they're both only London dispersion, this molecule is a little bit bigger. So these London dispersions are a little bit stronger than that one. And a stronger IMF is a higher boiling point. And then our last example here. Oh, we got another nonpolar molecule. So the strongest IMF will be London dispersion. This one is not polar. This one is not nonpolar. This is a polar molecule. Look at this asymmetry that we get off to the side here. So this is a polar molecule. So we know it'll experience dipole-dipole, but let's see if it meets the criteria of a hydrogen bond. And it does. We have a hydrogen bonded to either a fluorine, an oxygen, or a nitrogen. Okay. So because hydrogen bonding is stronger than London dispersion, this one would have a higher boiling point. All right, so I'm going to tell you right now, on this next example, there is a question that is so similar on the quiz. And students tend to struggle with it because they're not paying close attention to the wording. So let's go through a few of these together. You're going to notice that sometimes it's saying what holds molecules together, and sometimes it's going to say what holds atoms together. Oh, there's another one for atoms. Oh, this one says what holds ions together. Okay. So when we're holding molecules together, that's the IMFs, right? It's not the intra, it's not the covalent or polar covalent. It's IMFs. Let me get this model and show you. Okay, so we use these models, and there is an attraction between these water molecules. So here's the water molecule, here's the water molecule, and between them there's an attraction. That's an IMF. So whenever it's saying what's holding molecules together, then we need to pick one of the IMF options. So that could be dispersion. This is an IMF. Okay, so it could be a dispersion force. It could be hydrogen bonding, that's an IMF. Or it could be dipole-dipole, that's an IMF. Okay. So on this first one, it says, what holds two Cl2 molecules together? So I'm going to draw this for you. We have a Cl2 molecule. And it's not saying what's holding these atoms together. It's saying if there's more than one Cl2 molecule, what is the IMF attraction that's between them? We want to know what's between them. And I see a nonpolar molecule and a nonpolar molecule. So the strongest type, or the only type of IMF that occurs between them, is London dispersion. So B, dispersion. Okay. Now on this next one, it didn't say what's holding the molecules together. It's saying what's holding the atoms together in an HCl. So if I draw an HCl molecule, I don't want to know what the IMF attraction is to another HCl. I want to know what's holding these atoms together, this bond. And so this is not inter, it's intra. So our options for intra are either polar covalent or non-polar covalent. Okay. Now, if you look at the electronegativity difference between hydrogen and chlorine, there's a big difference there. And so because of that, it falls in the polar covalent range. So this is a polar covalent bond. Okay, let's look at a couple more of these. What holds atoms together in a nitrogen molecule? Oh wait, so this said holding atoms, so I know my options are either polar covalent bond or a non-polar covalent bond. Okay, and an N2 molecule looks like this. Oh yeah, they're triple bond with this one. Okay, so it's saying like this bond between the two nitrogens, is it polar covalent or non-polar covalent? Well, the difference in their electronegativity is going to be 0, right? Because they both have an electronegativity of 3.04. So that bond is nonpolar. Okay. Now, what holds two sodium chloride ions together? When it's talking ions, or it's a metal and a nonmetal, then we're specifically addressing ionic. So when it's ions or it's a metal and a nonmetal, then you automatically know it's ionic. The other one that's ionic, oh, there's a couple of them. Look here. Calcium is a metal, chlorine's a nonmetal. So since it's a metal and a nonmetal, that one's ionic. And then down here, we got iron, which is a metal, and oxygen, which is a nonmetal. So a metal and a nonmetal is ionic. All right, last two. The bonds that are broken when water boils. When water boils, it's still water, okay? So like it goes from being H2O liquid to being H2O gas. So that means that it was H2O in the beginning and it was H2O in the end. So we didn't ever break these bonds, okay? So the bonds were not broken. The IMF attractions between them, that's what we're overcoming. And we know from previous examples that water, the strongest IMF that it has is hydrogen bonding. So its IMF is going to be hydrogen bonds. So that's going to be C. And then we're going to skip this last one. I'll explain it really quick, but there's not a question like this on the quiz. What allows O2 to be dissolved in water so fish can breathe? It's still in the form of O2. So it's IMFs again, and they're nonpolar, so it'd be London dispersion. All right. Now that we've gone through that together, with your remaining time, what I want you to do is, it starts on page 17. Attraction between molecules, IMFs, worksheet number 1. This is the review for the quiz, okay? These are the proficiency targets that are really focused on, but they don't have questions right here. So it starts with number 1. And this ends on page 20. So I expect that you guys finish I want to see you get done with question 13. So 1 through 13. If you have time, feel free to keep going. But we are going to spend 20 minutes or so finishing this up next class, and then you're going to take the quiz. Okay, I will see you all next week.